So welcome, and now we are going to talk about time and space complexity analysis. And the main idea here is how do we decide between two algorithms. All right. So the important part here is if I give you two algorithms to solve a problem, how do we decide which one we would prefer and which one would be the worst algorithm for us? All right. So what do we care about? So we care about two things. We care about time, okay, and these are the main resources. Of course, there are other resources, but we use time and space. And by space, I mean the memory consumption. Okay, and time is usually the one that is the main concern for us. So a lot of algorithms are analyzed based on time. Space is also a concern, and often they are correlated. Algorithms that end up using more space generally end up using more time. Algorithms that end up using more time often end up allocating a lot of space. They are somewhat correlated in a rough sense, but we will study them as the two factors that help us tell us which algorithm should be preferred over which other algorithm. All right. Having said that, then the analysis of algorithms becomes really, really simple. Take an algorithm A1 and let's take a competing algorithm A2. Which one is better? Well, simple. Let's feed the same input. Okay. Let's run the two algorithms. Let's run the two algorithms and see which one is faster. All right. Now, this seems to be a very good way of comparing algorithms for all of 2 minutes, because then you ask yourself, what input should I choose here? What is the input? All right. Should this be a small input versus a large input? Who chooses this input? So maybe there are inputs in which A1 is faster, and maybe there are inputs in which A2 is faster. So maybe the designer of A1 comes in and says, hey, you took the worst possible input for me and the best possible for A2, and you ran this algorithm, shame on you. And we don't want to be ashamed of our choices, right? So in that case, there is a big question here. Which input do we consider for both algorithms? Number one. And number two is, how do we measure time? Well, on the face of it, this seems really simple. How do we measure time? Well, let's take our favorite computer and let's run it on some processor. Let's run this on the same CPU. Let's be fair, same CPU. Okay, same CPU, and then measure time. All right, that kind of works, but then the question is, who implements this algorithm? Remember, algorithms in this class have been taught in pseudocode. And does it make a difference which language do you implement this algorithm in? It definitely makes a difference. Certain languages have some constructs that make certain algorithms faster. Some languages like C are highly optimized, so if you spend a lot of time writing highly optimized C code or assembly code, your algorithm is going to work really, really fast. Of course, you're going to spend a lot of time doing it. All right. So the questions start to become bigger and bigger. So question is, how much time do you spend implementing each algorithm? Which language do you implement in? Who implements it? Is it a novice programmer? Is it a seasoned programmer? Do you have teams of thousands of people to implement? So when you look at these questions, you realize that comparing two algorithms and deciding between two algorithms is a very, very complicated question. And some of this complication is not going to be addressed in this class. Okay? So there is two kinds of comparisons. So there is comparing two implementations. And this is a very, very hard task. And in computer science, this goes under the name of performance analysis. And there is a lot of work on how do you analyze the performance of a computer program. We are not going to worry ourselves with implementations. in some language like C, C++, where it starts to depend a lot on the type of the language, the type of the runtime environment, the processors, how many cores you have, all of that comes into matter. We need to rise above all of those considerations. So versus comparing two algorithms. All right. Now when we look at comparing two algorithms, we really do not want to be bogged down by implementation details. Do not want to be bogged down by details, okay? And I'll put a star next to it, and you know exactly what details I'm talking about, all right? So I would like to know, how do we compare two algorithms? All right. Now, so in that case, let us make some assumptions. All right. So the first thing that we would like to assume is that both algorithms will be implemented, will be run, there will be a running time. But how do we measure running time? So one thing we could do is, running time is just the number of operations, number of basic operations. So we could give, for example, anytime I add two numbers, let me count that as one operation. Anytime I multiply two numbers, let me count that as one operation. This is not realistic. Computers may be able to add numbers faster than multiplying. I'll just count them as a single operation. Anytime I do a comparison, let me count that as one operation. Anytime I run an if statement, let me count that as one operation. Anytime I run a for statement, you initialize a counter, increment the counter, see if the loop is to end. So there is multiple things that we have to take care of in a for statement, and let's say each of these is a single unit operation. All right. So I'm going to simply count, instead of counting how much time it takes, I'm just going to count the number of operations. So I'm going to do an op count, something like that. How many operations that the algorithm runs to execute the program? Number one. Number two is, how do we deal with this problem of input? All right. And often enough, the input matters a lot. So we are going to treat inputs by their sizes. What does that mean? So that means that if, let's say, it's a sorting algorithm, so we are comparing, let's say, insertion sort against merge sort. If we are comparing insertion sort against merge sort, the inputs for both kinds of sorts is an array. So let us take the length of the array n to be the placeholder by which we are going to compare. So we are going to say, for an input of size 1000, how many operations did merge sort take, and how many operations did insertion sort take? Okay, so for an input of size 1000, you could say how many operations merge sort took, and you make a point there, and how many operations insertion sort took. Now the problem is, this addresses one problem, that there are large number of arrays and we don't want to deal with each and every array. This puts the number, this input size on the x-axis and the op count on the y-axis. So far so good. Okay, so op count on the y-axis and input size on the x-axis. The problem though is, which input, even if you look at a single size, let's say size 1000, there is a large number of arrays, infinitely many arrays of size 1000. Which of those arrays should I choose? All right. Now comes the second part of comparison. We could compare by best case. We could compare by worst case. Or we could compare by average case. Let me explain each of these in turn. So let us take a single algorithm now. Let's just talk about insertion sort. Okay. Last lecture we looked at insertion sort, and we saw that even for an array of size 1000, there is a difference. Okay. Insertion sort is really fast if the array is already a sorted array in the ascending order, already ascending sorted, it's going to run really fast. And we saw that it's going to take a large time if it is sorted in the reverse order, which means if the array is descending sorted, that's the worst case. Okay? If the array is descending sorted, that's the worst case. So there is going to be a spread. Even for a single input, there is going to be a spread which is caused by the large numbers of inputs of size 1000 that are possible. So of size 1000 that are possible, there's going to be a best array and there's going to be a worst array. All right? And the third thing is average, which means that if I put all arrays of size 1000 inside a bowl and I shake it and I randomly draw an array and I measure the time and I take the average of a large number of draws, there is going to be an average. Somewhere between the best case and the worst case, there's going to be an average. And the average here, I'm assuming there's a uniform distribution of inputs. I pick inputs at random, measure the number of op counts. I'm not going to measure time on a processor. I'm measuring op counts, and I'm going to count average. All right. So with that being said, there are three notions of time I could use for an algorithm. I could use the worst case time, I could use the average case time, I could use the best case time. Now, which one would you use? All right. So it depends on how you view the world. The best case, of course, is does it give you a good indication of the complexity? All right. Some people would say the best case is lame, right? But if I were going to sell an algorithm to you, let's say I was going to try to sell you on insertion sort, and I said the best case of insertion sort is if you have an array of size 1000, it can sort it in 2000 steps. And if you have an array of size n, it sorts it in 3n steps. Okay, so the best case is really, really good. And let's say based on my best case, you buy insertion sort. Question is, how likely is the best case to happen? And what you can show is that in insertion sort, the best case is super unlikely. If you have random arrays, what's the probability that they are already sorted or they are almost sorted? Very, very tiny probability. So people generally are very suspicious of the best case. Okay? Very few people I know do an analysis of an algorithm by best case. So that leaves us worst case and average case. So worst case is to give you a guarantee that's set in stone to say that no matter what happens, no matter what input you provide me, insertion sort is never going to exceed 2n squared operations. All right, if your input is of size n, I guarantee, and this is a guarantee you can write in a certificate, I will sign it, paste it on your wall, that says no matter what input you provide me, I will always take no more than this much time, and that time is the worst case time. And that's a very, very strong guarantee to provide. All right, and the third one is average case. There are lots of algorithms, and I will mention a few of them in this class, where the worst case is just too pessimistic. So the opposite situation happens, where the worst case is obtained by having an input that you would seldom see in practice. So if you want to capture the in practice, what happens in practice, you would use the average case. And the average case is mostly to say, let me tell you what the inputs on average are likely to look. So on average, you would get a random array, which is like randomized. I don't know, the inputs can come in any order. Any order is equally likely. With that being said, now you define a distribution over the inputs. You define a distribution. And based on this distribution, you can sum up all possible inputs times the likelihood of getting the input, the probability you would get them, times how many operations if you got that input, and that gives you the average case. As you can imagine, the average case is a little bit hard to pin down for many algorithms. The analysis gets complicated. It starts to involve probabilities, expectations, things that we love in the book and love to forget. Okay, I'm just kidding. But it's not everyone's cup of tea. It's not necessarily mine. I deal with it, but it's not my favorite subject. I don't take to it like a duck in water, and I'm sure many of you may share the same feeling with me. All right. So worst case analysis is easy often, and it's nice. It gives you an ironclad guarantee, but at the same time, it is going to be too pessimistic in some cases. an average case is maybe more desirable, but it's going to be hard to analyze average cases. Often, as far as I know, as far as I've seen in my 15 years here of experience, no one does best case. So let me ignore best case. It's very self-serving. Often algorithms will have very nice best cases, but don't get fooled by best cases. Okay, there is an application to best cases in something called proving lower bounds, but let's not worry about it. Worst cases and average cases are the things that we are often interested in. All right, okay. So to summarize this part of this lecture, we started off by saying, how do we compare algorithms? What's the metric to compare algorithms? Well, we like to compare algorithms by their resource consumption. So that is number one point in this takeaway from this lecture. Resource consumption includes time and space. It also includes other things like communication, but those are energy. Those are harder to analyze. We just use time and space as proxies for all those things. All right. So let's focus mostly on time. Space would be analogous. If I had two algorithms, there is one thing to compare the two implementations of the algorithm, where I implement them in C or C++. I decide what kind of runtime environment, I decide what kind of libraries, what kind of processor, what kind and who implements them, seasoned programmer versus novice programmer, and I compare the two implementations apples to apples by providing them the same input. That goes under a different name called performance analysis, and that's not what we will do in this course. In this course, we are going to compare two algorithms in their mathematical splendor without worrying about what happens when you implement them. But what we will see is that this gives you a flavor of how to compare algorithms, and in the next lecture I'm going to talk to you a little bit about this. Here we don't get bogged down by some of the details I just mentioned. Instead of getting bogged down by some of the details, we will count the number of operations. We will use what is sometimes called a cost model, which is to say how many operations does an addition count. Let's say one operation. Multiplication is one operation. Comparison of two numbers is an operation. An if statement is a single operation. For statement, let's say, has three basic operations: initialize, increment, see if the loop ends, and then the body of the loop, which I should mention counts when you execute the for loop. All right. And then the second idea was, okay, let's treat inputs by their sizes. Let's not think of the actual array that you're going to give the sorting algorithm. Let us more broadly talk about how does the running time depend on the size of the array. How does it grow with the size of the array? Now that you have a very nice axis, x-axis, which is the size, input size, y-axis, which is the count of the operations. Now that we have done that, we face the next problem, which is which input to choose. If I have n equals 1000, I have infinitely many arrays of size 1000. Which array should I feed to algorithm A1? Well, it turns out there's three choices: best case, worst case, average case. So we said no one does the best case because it's too self-serving. We talked about worst case and average case. Average case would be ideal, but a little bit hard to get to. Worst case is what we will end up for most algorithm, except for a few special ones for which we do average case. In the worst case, what we will find out is we get ironclad guarantees. They may sometimes be too pessimistic, but worst case complexity turns out to be a very good way of analyzing. And if you think about each n, there is a spread of possible running operational counts, op counts, or running time, which you'll use as a proxy for running time. The best case somewhere in the middle, the average case, and somewhere on the top, the worst case. Okay, in the previous lecture, we started arguing the foundations for what is called the asymptotic analysis. Okay, so we started to compare algorithms by either worst cases, average case, but not by their best cases because we said that's too self-serving. All right, and we defined a graph in which on the x-axis we plot n, the size of the input. On the y-axis we plot, let's say, the operation count, counting each operation by some cost model. Let's say addition costs 1, multiplication costs 1 of two numbers. Let's say comparison costs 1. So we have our price list here. for loop, we have our price list here. So based on the price list, we count the number of operations, and for every n, we would normally get a spread ranging from the best case to the worst case. And the worst case is the number of operations that the worst possible input, which takes the longest amount of operations. The best case is the best possible. Somewhere in the middle is the average case. All right. With all of this said, there is going to be then, and let's say we start from n equals 0, which say takes no time. So then there's going to be a curve. Okay, and this is going to be the worst case curve. Okay, and let's call this FWC of n. So this is a function that maps each input size to the number of operations of the worst case. And then there's going to be, let's say, an average case curve and a best case curve. All right, I'm not going to worry too much about the best case. There's going to be a curve about average case. And sometimes the worst case can deviate a lot from the average case. They don't have to be parallel to each other. But every algorithm, once you do subject it to this analysis, leads us to this curve. All right. So let us say, for example, insertion sort. The curve turns out to be f of n for the worst case. Let's just do worst case from now on. F of n for worst case is 0.05 times n squared plus, let's say, 2.5 times n plus 1.5. Why do you get fractional numbers? Maybe some of these operations are 1, but some of these operations are, let's say, half or quarter. All right, so you get a number like this. And let's say, for the sake of argument, this is what insertion sort gives you. And let's say merge sort gives you worst case complexity function, which is 2000 n log n. Okay, we saw last time that n log n was involved, plus, let's say, 1500 times n plus 20,000. I don't know why plus 20,000. Okay, let's just say it is. Okay, this doesn't make sense because at 0 this should be a 0. At 0 this is a 1.5. Just bear with me. I just wrote some function out. If you want, let's say log n here, defining log 0 as 0, which is not the case. All right. All right, something like this. All right, log n plus 1, just to avoid log 0. Log n plus 1. All right, something like this. All right, so this is the two functions, and I have done a lot of sweat to analyze the pseudocode and come up with these two functions. Now, the first thing you could question me is the cost model. Maybe addition is should not be the same cost as multiplication. Maybe multiplication should be twice the cost as addition. Maybe I have a really fast processor that optimizes multiplication to be like 1/5 the cost of addition. I don't know. So it all depends. So it all depends on the processor. So what that means is, one thing we will notice is then what is going to affect if we make a faster processor, let's say, that can multiply faster or do comparisons 10 times faster than an addition, or do a swap 15, but a swap is slow. Let's say the swap takes 15 ops, whereas a comparison takes 0.1 ops. All right. If you change your cost model, what's going to change is these constants in front of these numbers. All right, so these constants are going to change depending on your cost model assumptions. All right, whether you assumed an addition was a 1, multiplication was a 2, or an addition was a 1, multiplication was a 0.2, and a comparison was a 0.1, a swap was a 15 versus a swap is like a 0.01. Who knows, right? Based on the details of the processor, based on the details of the cost model, you still can change these constants. All right. And we would like to be independent of constants. Another way you can change these constants is if a clever programmer sees that 2 comparisons could have been replaced by a single comparison and saves you some constant factor in terms of comparisons, you could reduce the constant here. And we want to be independent of those details, like we said last lecture. We did not want to be bogged down by them. But turns out we are bogged down by them. So what I would like to do then is, once I get these kinds of worst case complexity functions, I would like to compare the two algorithms. Now I can compare insertion sort and merge sort, but something very strange is happening, right? Something very strange is happening. If I draw these two curves, Okay, let me draw the insertion sort curve in green. It's going to start fairly small, but it's going to go like that. If I look at the merge sort, it's going to actually start up here, but it's going to go like that. All right. Insertion sort in green, I should say green, and merge sort in red or pink. All right. Problem though is as n grows, initially insertion sort is doing way better than merge sort. It may even be hundreds or thousands of times faster than merge sort, but eventually merge sort overtakes and stays faster. So here is the overtake point, and here merge sort is definitely faster, and before the overtake point, let's say insertion sort is faster. It doesn't have to be this clean. Sometimes there could be like a few oscillations before you between who's faster before it settles down to one algorithm being faster. All right. Sometimes they could just be alternating between one algorithm and another forever. That's possible. All right. But this is how the graph between these two functions look. All right. So there are two takeaways I want to enforce. One is I do not want to worry about constant factors. Okay. This 0.05 versus 2000 I claim can be overcome by a clever programmer. Maybe. Okay. Let's take that as an article of faith right now. Okay. Number two is I am not very concerned about small inputs. I only care about large input sizes. Or there is another way of saying it, I only care about long-term trends. I don't care about short initial gains, I only care about long-term trends. And of course, this is a completely bad statement to say because maybe you're only interested in sorting arrays of size 500,000 and you are not interested in sorting arrays larger than that. Then your choice of which algorithm is better depends on which algorithm performs well for the range of inputs you're interested in. But let us say that for the sake of argument that we are writing an algorithm and we would like to see inputs that are as large as possible being handled by the algorithm. And this is not a theoretical statement. For example, about 50 years ago, when computing was invented, the size of arrays used to be maybe 1,000 or 10,000. Those used to be large arrays because that's how much memory a RAM, a big computer had in those days. And now, these days, you have gigabytes on your cell phone. All right, so things have changed a lot. The amount of memory has gone up, and therefore the size of arrays we can sort has gone up. In fact, the size of arrays we can store has gone up. Therefore, the size of arrays we can sort has gone up. And therefore, as time goes on, our algorithms will be expected to handle larger and larger inputs. So we are interested in knowing the behavior of the algorithm as the input size goes large. Ideally, as the input size goes through infinity. Maybe. All right. Even though we will try to avoid these kinds of limit notations in this class, I am interested in knowing which algorithm is faster asymptotically. Okay, and this is where the term asymptotically comes up. Okay, this is why we call it asymptotic complexity. I want to know which algorithm is faster. And remember, this is just the worst case. The best case, average case, they may have a different trend. I am not comparing them. I'm comparing the two algorithms in terms of, in the worst case, which one is still faster. All right. Okay. So now comes this idea that we should be able to ignore constant factors and large input sizes do not matter. Should not matter. Let me rephrase. Large input sizes matter to us better than smaller input sizes. So I'm more interested in inputs as the size goes towards infinity, or put another way, I'm more interested in trends. Okay. So this gives the need for using asymptotic notation. And what is asymptotic notation? Big O, big omega, and big theta that we have studied previously. And hopefully you have seen this. This is the less than equal to of comparisons between two things. This is like the greater than equal to, this is like the equal to, but with some caveats. And now we are going to justify those caveats in the light of this discussion in the very next lecture. See you then. Thank you.